In this episode, we will talk about AlphaEvolve, a coding agent for scientific and algorithmic discovery.
Right, and, discovering something genuinely new, whether it's in science or finding a faster algorithm, well, that's traditionally been a very human process.
Long process, too.
Oh, absolutely. Lots of brainstorming, trying things out, hitting dead ends, rethinking, experimenting, validating. It takes time.
And now we're seeing a lot of excitement around using large language models, LLMs, to try and automate parts of this.
Exactly. It's driven by how powerful these models have become, how well they handle language, and, the rise of AI agents that can actually do things like write and run code.
They've definitely sped things up in some areas, helping generate ideas or design experiments.
For sure. But the big hurdle, the real challenge, is getting these LLM systems to go beyond just assisting us. How do we get them to make truly new scientific discoveries or find genuinely novel practical solutions all on their own? That autonomous leap, it's been tough.
And that's where AlphaEvolve comes in, right?
Yeah, precisely. It's a really interesting approach, a coding agent that uses LLMs, yes, but combines them with evolutionary algorithms.
So like survival of the fittest, but for code.
In a sense, yeah. The main goal is discovering new algorithms, new solutions. And what's neat is sometimes the algorithm is the discovery, the main goal.
Like finding a faster way to sort data.
Exactly. But other times, finding the algorithm is just a step along the way. Maybe you need an algorithm to help you find some specific mathematical object or some configuration. The algorithm is the tool, not the final product itself.
I see. So it can aim for the algorithm or use the algorithm to find something else.
Right. And it's quite a step up from earlier work, like Fun Search, which you might have heard of. It also builds on ideas from robotics, finding control strategies, or symbolic regression, finding math formulas from data, and even synthesizing heuristics, those smart shortcuts for problem solving.
So what makes AlphaEvolve such a big step?
Scale and complexity, mainly. Earlier systems, like Fun Search, they typically worked on evolving maybe just one function or a pretty small chunk of code. AlphaEvolve is designed to evolve entire code files. We're talking multiple functions, different components, all interacting.
Okay, that sounds much more complex.
It is. It's a real jump in generality. If you look at Table 1 in the paper comparing it to Fun Search, well, the differences are clear.
Right, like whole files versus single functions.
Exactly. And hundreds of lines of code versus maybe 10 or 20. AlphaEvolve can work with pretty much any programming language, not just Python, like Fun Search.
And it can take longer to evaluate things.
Yeah, it can handle longer evaluation times using parallel computing, which is important for complex problems. And interestingly, it sometimes needs fewer samples from the LLM to get good results.
Does it need the best LLMs?
It seems to really benefit from the latest state-of-the-art LLMs. FunSearch didn't show as much improvement with bigger models. AlphaEvolve also uses much richer context in its prompts and can optimize for multiple goals at once, not just a single score.
That multi-objective part sounds useful.
It really is. Now, the flip side of relying on automated evaluation, which is a huge advantage for speed and objectivity, is that it works best for problems where you can write a program to automatically score a solution.
So domains like math, computer science, system optimization, where you can clearly define good.
Exactly. And that's where it's already shown some pretty stunning results.
Such as?
Well, in mathematics, it's matched or even beaten the best-known methods for several open problems. Things like the minimum overlap problem, kissing numbers. And in engineering at Google, it's improved scheduling in their data centers, optimized critical code for training AI models like matrix multiplication kernels, refined hardware circuits in their TPU's tensor processing units, and even sped up the attention mechanism in transformers.
Wow, okay. That's quite a range. So let's unpack how it actually works. Figure 1 shows it as this evolutionary pipeline.
Yeah, at a high level, think of it like this. The user defines the what. What problem are we solving? What does better mean? So they set the evaluation criteria, maybe provide a starting point solution, some background info.
And AlphaEvolve figures out the how.
Exactly. It figures out the algorithm, the steps, the code needed to get to an improved solution based on those criteria.
And figure 2 shows the loop. The database, sampler, LLMs, evaluators.
Right. It's an iterative cycle. The program database stores all the solutions found so far. The prompt sampler prepares instructions for the LLMs. The LLM ensemble, usually a mix of models, generates new code ideas. And the evaluator pool tests how good those new ideas are.
Okay, let's start with task specification. You mentioned the automated evaluation function, HA.
Yes, that's absolutely key. You need a function, HA, that takes a solution, the code, and output scores numerical metrics you want to maximize.
So for a math problem, H might run the code, maybe build a graph, check if it has the right properties, and return its size.
Precisely. Or, if you're evolving a search algorithm itself, H might run that algorithm for a set time and score how good a solution it finds. Or, for machine learning, train the evolved model and test its accuracy.
And users can mark which parts of their code should be evolved using comments.
Yeah, there's a simple API using comments like #evolveBlockStart and #evolveBlockEnd. Figure 3a shows it clearly. The code inside those blocks is the initial seed, the starting point for evolution.
And the code outside provides the context, the framework.
Exactly. It lets AlphaEvolve focus its efforts. You can even start with something really simple in the evolve block, like just returning a fixed value, and let AlphaEvolve build it up.
It sounds flexible in terms of what gets evolved, like raw code strings or specific functions or even whole search algorithms.
Very flexible. You can choose the level of abstraction. Raw strings give fine-grained control. Evolving constructor functions designed to build the solution, can be good if the solution has a nice, regular structure, like in FunSearch.
But for messier problems.
For messier problems, evolving a tailored search algorithm might be better. You can even co-evolve intermediate solutions and the algorithms to find them. It depends on the problem's nature.
Okay. What about prompt sampling? How does it tell the LLMs what to do?
Right, so AlphaEvolve uses these state-of-the-art LLMs and gives them pretty detailed prompts, often with lots of context. The key parts are examples of good solutions found previously, pulled from the database, and specific instructions on how to suggest changes.
Can the user add more context?
Oh yeah, you can add problem descriptions, equations, relevant code snippets, even research papers. There's also this idea of stochastic formatting, using templates with randomized phrasing to encourage variety from the LLM.
And it shows the LLM the results of previous attempts.
Yes, that's important. The prompt often includes the code of a past attempt, what happened when it ran, and its evaluation scores. It's direct feedback.
What's this meta-prompt evolution?
Ah, that's quite clever. It's basically using another LLM to help write the instructions and context that get put into the main prompt for the code-generating LLMs. So the prompts themselves can evolve and get better over time. These meta prompts are stored and evolved in their own database.
So it learns how to ask better questions.
Kind of, yeah. It refines its own prompting strategy.
Okay, so after the prompt comes creative generation.
Yeah.
The LLMs doing their thing.
Right. This is where the LM digests all that information, past solutions, instructions, context, and proposes new ways to improve the code.
And better LLMs lead to better results.
The paper makes it clear, yes. While it's model agnostic, performance definitely improves with more capable underlying LLMs. They're just better at understanding the context and generating useful, creative code suggestions.
How does it show the suggested changes? You mentioned diff blocks.
Yeah, usually it outputs changes in a standard diff format. You see the original code marked between search and HERNA, and the proposed replacement code between LM and replace. It's very clear what's being changed.
But sometimes it just outputs the whole new block.
Right, especially for very short code snippets or if a major rewrite is needed, it provides that flexibility.
And it uses an ensemble of LLMs, like Gemini Flash and Pro.
Yes, that seems strategic. Gemini Flash is faster, so it generates lots of ideas quickly, exploring broadly. Gemini Pro is more powerful, maybe slower, but capable of making those bigger, more insightful leaps.
So balancing speed and quality.
Exactly. Maximize exploration breadth with Flash, but still get those high-quality breakthrough suggestions from Pro. It optimizes the discovering process.
All right, so new code is generated, then it goes to evaluation.
Yep, back to that automated function H we talked about. It runs the new code and calculates the scores.
Are there ways to make evaluation more efficient? It could be slow for complex code.
Definitely. AlphaEvolve has options for that. One is an evaluation cascade. Think of it like stages of testing. Quick, easy tests first. Only if a solution passes those does it move to harder, more resource-intensive tests. Saves compute time.
Like filtering out bad ideas early.
Exactly. Another idea is using LLMs for feedback on things that are hard to score automatically, like code simplicity or elegance. The LLM gives a grade, which becomes part of the overall score.
Interesting. Using an LLM to judge the output of another LLM.
Yeah. And of course, parallelization. If the evaluation can be split up, it gets distributed across many machines in an evaluation cluster, speeding things up significantly.
You also mentioned optimizing for multiple scores is beneficial.
Right, even if you only really care about one primary metric. Why? Because programs that score well on different metrics might have very different structures.
Yeah.
Showing these diverse, good examples to the LLM in later prompts encourages it to explore different avenues.
Promotes diversity. Keeps it from getting stuck in one approach.
Precisely. It increases the chances of stumbling upon a truly novel solution that also happens to be great for your main goal.
Okay, evaluation done. Then the evolution step.
Yep.
Updating that database.
Right. The database stores the solutions and their scores. And the big challenge here, like in any evolutionary algorithm, is balancing exploration, trying new things, and exploitation refining the best things found so far.
How does AlphaEvolve manage that?
Its database algorithm is inspired by a few concepts. One is MAP Elites, which tries to find the best solution for various types of behaviors, not just the single overall best. Another is island-based models, where you have separate populations evolving somewhat independently and occasionally sharing good solutions.
So keeping diverse options alive while still pushing for improvement.
That's the idea. It helps avoid getting stuck too early on a decent but not great solution and encourages broader exploration of the solution space.
And this whole thing runs as a distributed pipeline.
Yeah, using a Syncio in Python, there's a controller managing things, LLM samplers doing the prompting and generation, and evaluation nodes doing the testing. They all run concurrently, asynchronously.
Optimize for throughput, not just speed of one step.
Exactly. The goal is to get as many generate evaluate cycles done as possible within the available time and budget. It's about maximizing the flow of discovery.
Okay, let's get to the results. Faster matrix multiplication sounds huge.
It really is. Matrix multiplication is fundamental, used everywhere from AI to graphics. Mathematically, it's about tensor decomposition.
And the rank is the number of multiplications needed. Lower is better.
Correct. Lower rank means a faster algorithm. Finding the minimum rank, even for small matrices like 3 by 3, is a notoriously hard, long-standing open problem.
So what did AlphaEvolve achieve? Table 2 shows improvements.
Yeah, it improved the state-of-the-art for 14 different matrix multiplication targets. The really big one was for 4 by 4 complex matrices. It found a rank 48 algorithm.
How good is that?
It broke a 56-year-old record. The previous best, Strassen's algorithm basically, needed 49 multiplications for that specific case in characteristic zero fields, which includes real numbers. Finding rank 48 was a major theoretical breakthrough.
Wow. And figure 4 shows how much the code changed to get there.
Yes, and figures 9AC zoom in. It wasn't just tweaking parameters. AlphaEvolve changed the optimizer, how weights were initialized, the loss function, hyperparameters. It evolved the entire search process over 15 steps.
Did human ideas help at all?
Interestingly, yes. For some targets, seeding the initial program with some human insights, like ways to add randomness or using evolutionary ideas in the starting code, actually boosted AlphaEvolve's performance further. It suggests a real potential for human-AI collaboration.
Very cool. Okay, what about discovering algorithms for open mathematical problems?
Right, this is another fascinating area. Lots of math involves finding objects, shapes, numbers, functions with optimal properties, packing shapes efficiently, finding sets with weird properties, things like that.
Where progress often means finding one better example than anyone's found before.
Exactly. So they applied AlphaEvolve to over 50 such problems across different areas: analysis, combinatorics, geometry.
And the results?
Pretty impressive. In about 3/4 of the cases, it rediscovered the best-known solutions. But in about 20%, 1 in 5, it actually surpassed the state-of-the-art. It found new, provably better constructions.
How did it do that? Did it evolve the constructions directly?
Mostly no. The key innovation here was evolving heuristic search algorithms. For many of these problems, checking a solution is fast. So AlphaEvolve would evolve a search program. That program got a time limit and the current best-known construction. Its job was take this good solution and find an even better one within the time limit.
So it evolved algorithms that are good at improving existing solutions.
Exactly. And often, the final record-breaking solution was found by a sequence of these evolved heuristics. Maybe one was good at making big initial jumps, another was good at fine-tuning near the end. It automatically discovered these adaptive, multi-stage search strategies.
That sounds incredibly powerful.
It is. It would be very hard for humans to manually design such specialized sequences of heuristics.
Can you give some examples of the new math results?
Sure. In analysis, improved bounds on autocorrelation inequalities. In combinatorics, a new upper bound for Erdo's minimum overlap problem, figure 10 shows that. C5R 0.380924, better lower bounds for sums and differences of finite sets.
What about geometry? Packing problems?
Yeah, better ways to pack hexagons inside a bigger hexagon, figure 11. New point arrangements in 2D and 3D that minimize the ratio of max distance to mine distance, figure 12. Improvements on the Heilbronn problem, figure 13. And a better lower bound for the kissing number in 11 dimensions, 593 now, lemma 1. Also, better circle packings in squares and rectangles, figure 14.
And these were problems suggested by top mathematicians.
Yes, people like Javier Gomez Serrano and Terence Tao suggested problems and helped frame them for AlphaEvolve. It really shows that synergy potential between human expertise and AI search power.
Amazing. Now let's shift to the practical side, optimizing Google's own systems. Data center scheduling.
Right. Google's Borg system schedules millions of jobs onto machines. Doing that efficiently is a huge optimization challenge, basically a complex version of bin packing. Wasted resources cost real money at that scale.
So AlphaEvolve evolved a scheduling rule, a heuristic.
Exactly, a relatively simple function shown in figure 6 for deciding which machine is best for the next job.
And it worked.
It did. Deploying this heuristic resulted in recovering about 0.7% of average compute resources across their fleet. That's significant at Google's scale. And importantly, they chose this approach over something like deep reinforcement learning, partly because the resulting heuristic was interpretable, debuggable, predictable, crucial for core infrastructure.
Makes sense. What about optimizing code for training models like Gemini, the kernels?
Yeah, training these huge models needs super optimized code, kernels running on TPUs. A key part is the tiling strategy, how you break down big matrix math into smaller chunks for the hardware.
That sounds tricky to get right.
It is. Engineers spend a lot of time tuning this. AlphaEvolve was used to optimize the tiling heuristics for a key kernel used in Gemini training, aiming purely to minimize runtime on the TPU, while guaranteeing the math itself remained correct. Figure 7 gives a sense of the problem.
So it found better ways to slice up the work for the hardware.
Essentially, yes. It also optimized arithmetic circuits within the TPU hardware itself. These are already heavily optimized Verilog designs.
Hard to imagine finding improvements there.
You'd think so. But AlphaEvolve found a simple code rewrite that removed some unnecessary bits, saving area and power, which the TPU designers confirmed was correct and useful.
And finally, optimizing compiler output directly for flash attention.
Right. Flash attention is an efficient way to implement the attention mechanism in transformers. Google's XLA compiler turns this into low-level code, intermediate representation, or IR. AlphaEvolve was applied directly to this compiler-generated IR.
And it found speedups.
Significant ones. A 32% speedup in the main flash attention kernel and 15% in the surrounding code. That shows it can even optimize the output of sophisticated compilers.
Okay, the paper also mentions ablation studies, testing which parts of AlphaEvolve are most important.
Yes, they systematically disabled different components to see the impact. Figure 8 summarizes this for matrix multiplication and kissing numbers.
What did they find?
Basically, all the key parts mattered. The evolutionary process itself was crucial. No evolution performed poorly. Context in the prompt was very important. No context hurt results. Meta-prompt evolution helped. Evolving full files was better than single functions. No full file evolution. And using powerful LLMs was better than just small ones. Small base LLM only.
So the whole integrated system works better than the sum of its parts, essentially.
That's a good way to put it. Each component contributes meaningfully.
The paper also situates AlphaEvolve relative to related work.
Yes, it discusses traditional evolutionary methods, other work combining LLMs and evolution, things like the AI co-scientist concept, LLM-based code optimization, and AI for science generally.
And how does AlphaEvolve stand out?
Mainly through its scale handling large code bases, its flexibility across domains and languages, and its reliance on programmatic, executable evaluation. Working directly with code avoids some potential LLM pitfalls like making stuff up, and allows for rigorous testing.
So in the discussion, they circle back to the power of combining LLMs, evolution, and automated evaluation.
Right. They emphasize how this combination has led to real discoveries in math and practical gains in complex systems. They also mention the potential for AlphaEvolve to help improve its own infrastructure, maybe even the base LLMs, though the gains there are more moderate so far, as the feedback loops are longer.
And the main limitation is still needing that automated evaluator.
Yes, that's the key bottleneck currently. It's great for math, CS, optimization, but harder for fields needing physical experiments or subjective human judgment. Though they do point to ongoing work using LLMs as evaluators, which could be combined with AlphaEvolve in the future, maybe LLMs for high-level feedback, then code execution for rigorous checks.
So AlphaEvolve is a really potent approach for automated discovery via code evolution.
Absolutely. It's a significant step in using AI to tackle tough scientific and engineering problems by evolving code.
So AlphaEvolve has demonstrated a remarkable ability to make genuinely new discoveries in well-established scientific and computational domains by evolving computer code. It's truly fascinating to consider the potential of this approach to accelerate progress on long-standing open problems in mathematics and to optimize the critical technologies that form the foundation of our increasingly digital world.
This leads to a compelling thought for you, our listener. Considering the rapidly increasing sophistication of AI coding agents like AlphaEvolve, what previously seemingly intractable problems in science, engineering, or even other fields might now be within our reach? And how will this burgeoning ability to automate discovery and optimization fundamentally reshape the landscape of scientific and technological innovation in the years to come?